Okay, so the application of Biot Savart law, first application of Biot Savart law, that is the magnetic field at the center of the current carrying circular coil. Before that, we are going to be talking about what is current element. So before all of that, we're going to be drawing a small section of the wire. Let's this is DL, right? So what is the volume of the wire? ADL, right? ADL is the volume of the wire, where A is the cross-sectional area. Then what is so basically there are charges flowing in it. There are n amount of charges flowing through this, and Q, n is the total amount of charges per unit volume, and then this is basically dq equals to this. So now we're going to be, this is basically the charges flowing through this small section of wire, DL section of wire. And now we're going to be looking at this is dq, right? And we know the current is flowing there. So the current, the charges will be flowing at a velocity of vd, because the current is there. How is current created? Through drift velocity of the free electrons. We have already learned that. Now we are going to be looking at the basically this formula. V is equals to Q, right? QV sine theta by R square. Now using this formula of the moving charges, this is basically dB, due to this small section of wire, will be it's equals to dq vd sine theta by r square, where r is the radius of the wire, right? Now talking about radius of the wire, not radius of the wire, radius of the circular coil carrying current. Now we're going to be looking at dB is equals to a dl n q vd sine theta, right? This is sine pi r square. Now what is current? It is a nq vd, right? So basically this is I dl vector sine theta pi r square, right? Now talking about this, this is the formula of the Biot Savart law. Now looking at the first application on top, this is basically the magnetic field due to current carrying coil at the center of the current carrying circular coil. Now we see the angle between IDL and R is 90 degree, and from the thing we know, what was it, B, oh, I forgot something over here. This is mu naught by 4 pi. I almost forgot about it, and now this formula is incomplete. It will be naught by 4 pi. Now this formula is complete, right? This is B is equals to mu naught by 4 pi dB is equals to dB vector is equals to mu naught by 4 pi IDL vector cross R vector by R cube. Now this is the vectorical form of the Biot Savart law. Now talking about the current carrying coil, this as you can see from this formula, this theta is the angle between the IDL current element and R. Now what do we see over here? The angle is 90 degree and sine 90 degree is 1, so we get IDL by R square mu naught by 4 pi. Now how do you get B due to the whole coil? Well, we know this is R. What is the circumference of the coil? It will be 2 pi r. So we're going to be integrating this formula, definite integral, and then this will be 2 pi r 0. Now talking about this, we can integrate it very easily. It will be mu naught, I mean B is equals to mu naught pi 4 pi, and then this is IDL. It will be bang over here. It will be into 2 pi r, pi r square. In the end, the actual formula will be, let me just do freehand, b is equals to mu naught by 2 into I by r, IDL by r. So this is the formula for the circular coil carrying current and the magnetic field at the center of that. Alright, so how do you find the direction of this magnetic field? That is very easy. We're going to be looking at the vectorical form, IDL cross R. We can use the right hand rule, and then we can also use the right hand curl rule, or we can also use the same old reliable vectorical method. So it will be it is IDL cross R, right? And the ideal right now in our case, it's basically over here. It's going over here. It's the current is flowing anti-clockwise. The radius vector is over here. We will be measuring it in the center of the coil. If we are measuring it over here at point P, the radius vector will be like this. This will be the small r vector, but we're measuring at the center of the coil, which means r will be equals to r. So in this case, this is minus I vector, this is minus j vector, right? So it will basically be outwards. The current, like the magnetic field, will be outwards because it is I cross j, which will be equals to positive k, because minus minus gets cancelled, and then I into j will be k from this formula, I j k. So we can use this kind of method to find any direction for any formula, right? Even Biot Savart Law second application, or the third application, the solenoid or the toroid, right? And then this was what do we use here? It's k, so it's going outwards. We can also use the right hand curl rule. So basically the current is going outwards, so we're going to be looking at that, and then the direction of the magnetic field will be going outwards towards the positive direction, and you assume the positive direction, right? So now we're going to be looking at a small section of this single thing. Now we have found due to the whole circular carrying coin. What about the semicircular carrying coin? It's basically the same, but in the integral part we only do pi r 0, because due to this the current is not really flowing. It will only be flowing over here, right? So we're going to be integrating this half part. It will be pi r by 0, and then even for this it will be theta, and then we can also and we just need to change this value. We have to change the upper limit of the integral, and we can find, what can we find the arc, right? So over here it's pi because it's the semicircular, but what if we use theta, right? So it will be theta. We're basically using this, and the theta is in radian. If you did not know, right? The theta is in radian, so we can use this upper, like the integral, and we can use theta r by 0, and then we just need to make changes to the integral to find the magnetic field due to semicircular, or basically the some section of the wire. And that's it. This is the Biot Savart Law's first application. About the units and all, you probably know it. I'm not going to talk about it, but this is the overall explanation of the Biot Savart Law second application. First application. Now we're going to be looking at the second application, which is better. And then the third application, not the third application, but we're going to be looking at the solenoid is better. So that's